In this video, we are going to start our section on the graph of a function. So our goals are to sketch the graphs of common functions and to recognize when a graph has a hole and how do we sketch the graphs of functions with holes. So in this video, we are going to introduce the graphs of some common functions. So there's 6 very common function graphs. And I've written those functions here and I have blank axes for each of them. What I want to have you do at this point is give the video a pause for 3 minutes. Try drawing as many of these as you can based on what you remember from algebra class. Remember, if you get stuck on something, you can get a sense for the graph by plotting some points. Like for the first one, if I plugged in x equals -2, y would be the absolute value of -2, which is +2. And that would tell me 1 point on the graph. But at this point, let's pause it for 3 minutes and try as many of these as you can. Pause in 3, 2, 1. Pause it and try it. Okay, so hopefully you did that. Hopefully you paused it to try it. Let's talk about them. So my absolute value of x graph, this has this upwards V shape. So it goes this way, then it kind of has this point, and then it goes upwards like this. So my absolute value of x graph. So it goes through the origin, and this point at the origin is called the vertex. Very much like in a parabola, and that's the one we're going to draw next. We've seen this one before. So y equals x squared, that's our upward-facing parabola. Upward-facing parabola. This point in the middle, at 0, 0, we call that the vertex. Okay, so we got the first two. We're on to y equals x to the third. So the x to the third graph, it also goes to the origin, and then it goes kind of slowly upwards like this, starts to curve like this, and then it does something very similar in the third quadrant, except curving down. So this also goes through the origin, 0, 0, but for x cubed, we call that an inflection point instead of a vertex. So an inflection point. So an inflection point, you'll learn more about what these are in calculus, but the key idea is it's a point where the graph changes how it's curving. So on the left of the inflection point, the graph is kind of curving downwards, and then on the right, it shifts to curving upwards. So that shift in how it's curving is what classifies an inflection point. All right, so before we do these other 3 graphs, let's fill in this key information about domain, range, and symmetry. So the domain for this, well, there's 2 ways I can see it. Either from the formula, I think about the restrictions on x. Is there anything I can plug in that would make this undefined? And the answer is no, right? There's no denominator. There's no even roots where I got to worry about a negative inside. So that means the domain's everything. Domain is -infinity to +infinity. I can also see it from my graph if I think about what are the x values in the graph. And x can, be any negative number going this way. It can also be any positive number going this way. And it can be 0 right at the vertex. So that's also how I can see the domain is anything. The range, my y values, start at 0, and then they can be anything bigger than that, anything positive. So my range starts at 0 bracket onwards to infinity. And this graph is the mirror image of itself across the y-axis, so it has symmetry about the y-axis. So symmetric about the y-axis. Now for x squared, for my domain, well, my x values, if I look at the graph, well, it's hitting every x value. Nothing is skipped. I can also see from the formula that there's no restrictions. I can plug in any number for x. So domain is everything, -infinity to +infinity. The range also starts at 0, and then anything bigger than that I can achieve. So bracket 0 onwards to infinity. This is also symmetric about the y-axis, right? It's the mirror image of itself across the y-axis. All right. So for x cubed, my domain, my x values, is everything, -infinity to +infinity. We hit every single x value along the way. There's no x value that's skipped. My range, my y values, well, I can hit all the negative y values down here. I can also hit the y value 0 at the inflection point, and then I hit all the positive y values going this way. So the range is also -infinity to +infinity. And then this is symmetric about the origin. It's the mirror image of itself across the origin. And what that means is if I take any point on the graph and I draw the mirror image of it across the origin, well, that's also going to be a point on the graph. So that's true no matter what point that I take. If I draw the mirror image of itself across the origin, that's another point on the graph. All right, let's talk about the bottom three. So square root of x. So the square root of x graph kind of starts at the origin here, and then it curves upwards like this. So I call this, so this is 0, 0, and for the square root, I'm going to call that starting point, the initial point where my square root function begins. So my domain, my x values start at 0, bracket, because I do achieve the x value 0, and then they get bigger and bigger and bigger. They go onwards to infinity. I can also see that from the formula, if I think about restrictions, well, the x has to be greater than or equal to 0, and that's what gives me this domain. My y values start at 0 at this initial point, and then they get bigger and bigger and bigger. So the range is also bracket 0 to infinity. Let me make this parentheses better here. Symmetry? Well, this one doesn't have any symmetry, so none. It's not symmetric about the x-axis or the y or the origin. Like, for example, if it was symmetric about the x-axis, there would have been another part to the graph here, but that's just not there. Okay, so what about y equals 1 over x? So this graph has two pieces. It's got one piece here in this first quadrant, and it's got a mirror image piece down in the third quadrant. So this graph is what's called a hyperbola. And if I plot a couple points, if I plug in x is 1 into this, I'll get y equals 1 divided by 1, which is 1. So the y value there is also 1. And if I plug in -1 for x, I'll get 1 divided by -1, which is -1. So the y value there is -1. So these are 2 points on my 1 over x graph. So my domain, well, if I look at the graph, there's one x value that gets skipped. And that's when I reach x is 0, because I have an asymptote there. But every negative x value I'm getting, every positive x value I'm getting, I can also see from my formula that, wait, the denominator x better not be 0. So the domain is everything except 0. So that's -infinity to 0, parentheses, union, parentheses 0 to infinity. For my range, for my y values, there's also one y value that gets skipped. And that's the y value 0, right? Because I hit all the positive y values over here. I hit all the negative y values over here. I just don't reach the y value 0. So the range is also -infinity to 0, union, parentheses 0 to infinity. This graph is symmetric about the origin. It's the mirror image of itself across the origin. So about the origin, and it has some asymptotes. It's got this vertical asymptote at the y-axis. So the equation of that line is x equals 0, right? Because every single point on this vertical line has x coordinate 0. It has a horizontal asymptote. So horizontal asymptote is on the x-axis. And every single point on that horizontal line has the same y value. Y equals 0. And that's the equation of my horizontal line. All right, so we got one more of these. And this is, I think, the hardest to remember, the most complicated graph. But nonetheless, we can handle it. So when I have like a square root of some number minus x squared, there's something I can do with this equation to help me remember what the graph is going to look like. I'm going to first square both sides to get rid of the root. That'll give me y squared equals 1 minus x squared. And now let me add x squared over this side. So that gives me x squared plus y squared equals 1. And this is the formula of something I've seen before. This is a circle. This is a circle. Now, the center of this circle is 0, 0, because the x coordinates, what do I plug in for this to make this 0, and that's 0. The y coordinates, what do I plug in here to make this 0, and that's 0. R squared is 1, which means the radius is 1. But it turns out when I kind of go backwards, when I go backwards and do this this final step. When I square root both sides to get this, typically I would get a plus or minus when I square root both sides. So if I were to go from here back to this step, I'm going to get two cases. I'll get y equals the positive square root of 1 minus x squared. I also get y equals negative square root of 1 minus x squared. And it turns out that when you have the positive square root, that gives you the top half. This is going to be the top half of the circle. And the negative square root, like this, gives you the bottom half. So why is that? Well, I'm going to graph it first. So I had the positive square root. That's going to be the top half of the circle. So top half of the circle centered at the origin, radius 1. So that means this is 1, 0. On the other side, that's negative 1, 0. Up top, that's 0, 1. We sometimes call those extreme points on the circle the poles. So at the left, the right, the top, and the bottom, the poles. And the reason I know this is the top half rather than like the right or something like that is this is saying y equals this positive square root. Well, whatever I plug into the square root, the number I'm going to get out is non-negative. So this is saying y is non-negative. That has to be this part of the circle because that's where y is non-negative. Okay, so key tip, if we see a square root of like a number minus x squared, square both sides to identify what the underlying circle is. So then I can figure out, oh, where is it centered? What's the radius? Because I know I have a semicircle. So my domain, my x values start at -1 and they go until +1. My y values start at 0 and then they go until 1 at that point up top. Symmetry, this is symmetric about the y-axis. And there we have it. These are our 6 common graphs.